Welcome back to the deep dive. Today, we're strapping in for a really fascinating journey, I think, right into the foundations of physics. We're exploring this concept, symmetry, that connects, well, abstract theories to very real conservation laws. Our guide is Chapter 52 from Feynman's Lectures, Vol.1. It's called Symmetry and Physical Laws. Our mission really is to get a feel for nature's laws by asking, what happens if we, transform the whole universe, move it, spin it, mirror it, scale it? Which laws stick, and crucially, which ones don't?
Exactly. That idea of sticking or staying the same is invariance. That's the core. When physicists talk symmetry, it's not just about, say, a crystal looking the same when you rotate it. It's about the laws themselves. Does the physics look identical after you do something in operation to the whole setup? What stays constant invariant no matter what?
Right. And we'll start with the really neat perfect symmetries, the ones that give us these fundamental truths. But we're building towards something unexpected, a real shocker, historically speaking, where a symmetry everyone just assumed was true mirror reflection turned out to be, well, broken.
Yeah, that's later. Let's start with the solid ground. The symmetries where the laws are invariant. Feynman calls them the basic operations. Foundational stuff. First up, translation in space. Basically, the laws of physics don't care where you are. Run an experiment here, run it on Mars, run it in another galaxy. The underlying rules, gravity, electromagnetism, all that, they're exactly the same. Location doesn't change the fundamental laws.
Okay, makes sense. Physics is universal. And what about time?
Same deal, translation in time. This is huge. It's the assumption that lets science even work. Really, the laws were the same yesterday, they're the same today, they'll be the same tomorrow. It's why we can repeat experiments and trust the results over time.
Right. Otherwise, how could you build on anything?
Exactly. Then there's rotation in space. Turn your whole lab setup by, say, 30 degrees, or any angle. The physics inside doesn't change. The laws are isotropic, no preferred direction in space.
Okay. And the last big one.
Uniform velocity, this one comes from Einstein, relativity. If you put your lab in a box and move it at a constant speed without acceleration, all the physics experiments inside will give the exact same results as if it were standing still. That's the Lorentz transformation invariance. Pretty remarkable.
Okay, so space, time, rotation, constant velocity.
Yeah.
These things don't change the fundamental rules. But, why is identifying these symmetries so important? What does it buy us, physically speaking?
Well, that is where it gets truly elegant. This is maybe one of the deepest connections in all of physics. As Feynman really emphasizes, these symmetries aren't just descriptive, they demand something. Each symmetry directly leads to a conservation law.
Okay, so the symmetry isn't just a pattern we notice, it causes a conservation law.
Precisely. It guarantees it. Look, time symmetry, the fact that laws don't change over time, that's what guarantees the conservation of energy.
Wow. Yep.
Space translation symmetry laws are the same everywhere that guarantees the conservation of momentum. And rotation symmetry laws don't depend on direction that guarantees the conservation of angular momentum.
That's incredible. So just by knowing the laws don't care about when or where or which way, you automatically get energy, momentum, and angular momentum being conserved.
Exactly. It's built into the fabric of things. And it even extends to quantum mechanics. There's a symmetry there related to the phase of the wave function, a bit more abstract. But that symmetry corresponds directly to the conservation of electrical charge. So yeah, symmetry is fundamental to stability and predictability in the universe.
Okay, that's the beautiful side. The perfect symmetries leading to perfect conservation. But now we get to the wrinkles. Let's talk about a transformation that feels like it should be symmetrical, but isn't. Scale. Changing the size.
Right. Intuitively, you'd think if you build a small working model of something, you could just scale it up perfectly, make it 10 times bigger, and it would work the same way, just bigger.
Yeah, seems logical.
But it absolutely doesn't work. The laws of nature are not symmetrical under a change of scale.
Feynman's example is brilliant here. The matchstick cathedral.
Right.
You build a little one, it stands up fine. Then you try to build one 5 times bigger in every dimension, using scaled-up matchsticks, essentially. What happens?
It collapses under its own weight. Pow!
Why, if it's perfectly scaled?
Because the laws governing strength and weight don't scale the same way. This is crucial. When you scale up a structure, its strength generally depends on the cross-sectional area of its supports. Area scales as the square of the size increase.
Okay, so 5 times bigger means 5 squared, or 25 times the area, so 25 times stronger.
Right. But its weight depends on its volume, and volume scales as the cube of the size increase.
So 5 times bigger means 5 cubed. 125 times the volume, 125 times the weight.
Exactly. The structure is 25 times stronger, but it's 125 times heavier. The weight completely overwhelms the strength gain.
Whoa.
That's why you can't just scale things up indefinitely. Gravity, material strength, these things impose a natural scale. You can't have house-sized ants, for instance. Physics forbids it at that scale. Their legs would snap.
So scale invariance is broken. We can move, rotate, weight. But we can't just resize the universe and expect the physics to stay consistent. That's our first broken symmetry.
Yep, a fundamental limitation based on how forces and dimensions relate.
Okay, now for the big one. The one that really shook things up in the 20th century. Reflection. Mirror symmetry. Also known as parity, or P. For ages, everyone just assumed the laws of physics were ambidextrous, that there was no fundamental difference between left and right built into the laws themselves.
That's right. The idea was, if you perform an experiment and then you imagine building its perfect mirror image swap, all lefts for rights, rights for lefts, that mirror image experiment should be perfectly possible according to the same laws.
Like looking at a clock in a mirror. The mirror clock seems to run backwards, maybe, but the mechanism could theoretically be built, right? Left-handed screws instead of right-handed ones, but physically possible.
That was the assumption. The laws themselves shouldn't care about handedness or chirality.
But then you look at biology. You mentioned amino acids earlier, L-alanine versus D-alanine. Life on Earth uses only the L form, the left-handed version. How did physicists explain that away if the laws were supposed to be symmetrical?
Well, for a long time, the thinking was it was just a historical accident. Like maybe the first life forms just happened to pick alanine and everything
Yeah.
evolved from there. The laws allowed either, but chance picked one.
So the initial conditions were biased, but not the underlying rules.
That was the hope. But to really test the laws, you have to look carefully at how physical quantities behave under reflection. Feynman distinguishes between two types of vectors here. You have polar vectors, things like position, velocity, force, momentum. When you reflect them in a mirror, they reverse direction. A velocity vector pointing right becomes one pointing left in the mirror image. But then you have axial vectors. These are usually related to rotation. Think of angular momentum like a spinning top or a magnetic field created by a current loop. When you reflect these in a mirror, they actually don't reverse their essential direction relative to the system. A clockwise spin still looks like a clockwise spin relative to its axis in the mirror.
Okay, that's a bit trickier to visualize, but I get the distinction. Polar vectors flip, axial vectors don't.
Right. And for the laws of physics to be truly mirror symmetric, parity conserving, they had to work perfectly even when you flipped the sign of all the polar vectors but kept the axial vectors the same.
And for electromagnetism, gravity, the strong nuclear force, it seemed to hold for centuries.
It did. Everyone assumed it was a universal truth. Until the weak interaction, the force responsible for things like beta decay and radioactivity.
This is where the story takes a sharp turn.
A massive turn. In the mid-1950s, theorists T.D. Lee and C.N. Yang started questioning this assumption. They looked at the existing data and realized, hey, nobody's actually tested if parity holds for the weak force. They proposed it might be violated.
And then came the experiment, the famous Wu experiment.
Yes, led by Chien-Shiung Wu in 1956, confirming Lee and Yang's suspicion in 1957, it was revolutionary. It proved Kacher does have a preferred handedness, at least where the weak force is concerned.
Okay, walk us through it. How did they show the mirror image wasn't real, physically?
They used cobalt-60 atoms, which undergo beta decay. They spit out an electron. They cooled these atoms way down, near absolute zero, to minimize thermal jiggling. Then they used a strong magnetic field to align the nuclei spins. Think of them like tiny spinning tops, all lined up, spinning in mostly the same direction. Remember, spin is an axial vector.
Got it. A line spins. Then what?
Then they watched where the electrons came out as the nuclei decayed. Now, if parity symmetry held, if the mirror world was just as valid as the real world, the electrons should have been emitted equally in both directions along the spin axis. Up or down, same probability. The setup and its mirror image should behave identically.
Because the mirror image would just flip the direction the electron goes, a polar vector, but not the spin direction, an axial vector.
Yes.
So symmetry would mean no preference.
Exactly, but that's not what they saw.
What did they say?
They saw that significantly more electrons were emitted in one specific direction relative to the nuclear spin specifically, opposite to the direction of the magnetic field that aligned the spins.
Whoa. So a definite preference. An asymmetry.
A clear asymmetry. The mirror image experiment, where electrons would preferentially fly out the other way, simply doesn't happen in nature with the same probability. The weak interaction fundamentally distinguishes between left and right.
That's profound. It means physics itself contains a definition of left-handedness and right-handedness. It's not arbitrary.
It absolutely does. It turns out the electrons emitted in beta decay are predominantly left-handed. Their spin is oriented opposite to their direction of motion. The mirror image, a right-handed electron from this decay, is much less likely or essentially forbidden by the weak force as it operates.
So parity P is broken. Just like that, a fundamental symmetry gone.
Yeah.
What do physicists do then? Just accept a less symmetrical universe? Or is there another trick?
Well, this is where it gets even more interesting. If one symmetry is broken, maybe combining it with another operation could restore the balance. This brings us to antimatter.
Ah, right. Particles with the same mass but opposite charge and other quantum numbers, like the positron, the anti-electron.
Exactly. So there's another operation we can consider, charge conjugation, C. That's the operation of swapping every particle in your system with its corresponding antiparticle. Electron becomes positron, proton becomes antiproton, and so on.
Okay, so we have P, reflection, swapping left-right, which is broken by the weak force. And we have C, charge conjugation, swapping matter-antimatter.
The next question was, what if the universe isn't symmetrical under P alone, or C alone, but it is symmetrical under the combined operation CP?
Meaning, if you reflect the experiment in a mirror, P and E, simultaneously swap all particles for antiparticles, C, then does the physics look the same?
That was the hope. And for a while, it seemed to work. The evidence strongly suggested that CP symmetry was conserved, even by the weak interaction. It was like the universe compensated. A left-handed electron doing something via the weak force behaved essentially identically to a right-handed positron doing the mirror image anti-something. The violation of P seemed to be perfectly canceled out by also invoking C.
So the strong force, electromagnetism, they respect P and C individually. Yeah. But the weak force breaks P, breaks C, but seems to respect the combination CP.
That was the picture for a time, and it's largely true for most processes Feynman discusses here. The main point is that the weak force is the odd one out, breaking these fundamental mirror symmetries, relying on this combined CP symmetry to maintain a deeper kind of balance. Though, side note for listeners familiar with later physics, even CP was eventually found to be slightly violated too, but that's a story beyond this chapter.
Wow. Okay, so this chapter takes us on quite a ride. From the perfect symmetries of space and time giving us bedrock conservation laws, through the very practical breaking of scale symmetry, you just can't build infinitely big things,
Right.
to the absolute shock of realizing the weak force violates mirror symmetry, that nature has a built-in handedness.
It really forces you to rethink what fundamental means. We start with these beautiful, intuitive ideas of symmetry, but nature turns out to be more subtle, more complex. That assumed perfection isn't always there.
And Feynman leaves us with a really interesting thought, doesn't he? Almost philosophical.
Yeah, about near symmetry. Why does nature seem to get close to perfect symmetry so often, like planets in almost circular orbits, or this near-perfect CP symmetry, but rarely achieve it perfectly?
Is perfect symmetry even the goal? Or is it the slight imperfections, the broken symmetries like scale and parity, that actually make the universe interesting, dynamic, and capable of complexity?
That's the question to ponder. Maybe the breaks in symmetry are just as important as the symmetries themselves. It gives the universe character, you could say.
A fantastic place to leave it. Something for all of you to think about as you look around at the world, maybe even your own hands. Are they truly symmetrical? And does it matter? Thank you for joining us for this deep dive into the often surprising world of symmetry and physical laws.